This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Thanks, Giorgio, and morning, everybody. And as ever, do please chip in with any questions as necessary. Now, when I talk about concrete, most of you probably think straight away about the structure of concrete you see around you, solid grey material used for slabs and beams and so on. But the origins of concrete are very different. Of course, it was not originally reinforced, and it was not originally made with Portland cement. It was a soft material made with materials like lime, even sometimes plaster. So the evolution of concrete as we now understand it is quite a long and complicated process. And I want to begin by talking about the use of lime, which is the basis of all of this. Lime is obtained from calcium carbonate. You probably know this broadly, but let's go over it. Calcium carbonate might be limestone, but it can also be things like shells or coral, various other materials. And you produce lime by burning it, by heating it, and you then you drive off the carbon dioxide and get quicklime, calcium oxide. Now, bear these terms in mind. Quicklime and slaked lime are the two things. Quicklime is calcium oxide. It's a rather caustic material. It's dangerous to handle. And for normal uses, it's hydrated. That is, it's mixed with water. And that's the second process you see there. Giving off a lot of heat, and you get a rather more inert material which you can use for building purposes. So that's slaked or hydrated lime. When you've used it, when you've mixed it in your cement or your stucco or whatever material might be, over time it absorbs carbon dioxide again from the atmosphere and hardens. So you've actually gone back again in the third process, back to what you had before. You end up with calcium carbonate that you started with. So you've created an artificial limestone over a period of time. Now, the other thing to mention is that this is a fairly slow process. So lime takes quite a long time to harden. And also, because it hardens from the outside, the carbon dioxide is accessible from the outside. If it cracks, the building shape shifts. It can heal itself because the inside is exposed, and you get new calcium hydroxide ready to be carbonated. So that's the process. It's called the lime cycle, going from calcium carbonate back to calcium carbonate once again. Now here's an example of a lime mortar between stones. There's the question, what are those white pieces in it? You all there?
Is it quartz or like an aggregate?
Now, they're shells. This is shell lime, very commonly used in Australia. In Australia, very commonly used because there were huge middens of shells left by the Aborigines from feasting on shellfish. So in the early settlements, a lot of this material was used. So that's what it is. It's from a building in Windsor, New South Wales of the 1840s. Here's how you burn the lime. Now, there are a huge variety of lime kilns. You can, in fact, burn it just on the ground if you put enough material around it, like sods or other material to enclose it. But you get a very heterogeneous material. You can burn it in a pit, which is quite commonly done. But best of all, you make a kiln like this one. So you have usually a conical sort of kiln, a kiln that slopes towards the bottom. And you build the limestone up inside it in a sort of temporary structure, leaving a space for the fire within. And you burn it for some time, maybe a couple of days before it's burnt through. And you then draw the lime off. So you tend the fire from the bottom, you actually put fuel in, and you draw the fuel off from the bottom as well. That's the basic sort of lime kiln. There's another version, really doing the same thing, just different shape, but from a classical description. Now, it's better if you can bring your limestone to the top of the kiln and drop it in from the top. It's much easier to load the kiln. You can't pile it up from inside, from the bottom. So most kilns of any sophistication have a way up to the top where you can drop the fuel in from the top. So you drop it in from the top and you draw it out from the bottom at the end. Here's an example in Australia, rather different shape. This is called a D kiln, and they're used mostly in New South Wales and Western Australia. So you see the top is near ground level, so you can drive your cart up with the limestone and put it in. but there's an exposed face at the bottom. We get access to the bottom doorway. It's called a D kiln because one side on the left is straight and the other side is curved in the shape of the letter D. This is what's more common in Victoria, more common perhaps worldwide, is a totally circular kiln. But the same thing, you come in at the top, there's an exposed face on the right-hand side there, so you can draw the lime out from the bottom. This is a comparative diagram, but rather misleading because the D kiln isn't shown as the letter D. It's shown what it basically is. It's a rectangular kiln at the top center, but it should have those curved corners I pointed out on the face away from the loading face, from the unloading face. So there's the pit kiln on the left, very primitive kiln, and so on. They're all basically doing the same sort of thing. When you get to the bottom right, though, you have a continuous feed kiln. Now, the idea of this is that rather than burn the lime, unload the kiln, start off again, is you go on feeding fuel in, feeding limestone in, and drawing the burnt lime off continuously, and it's a more industrial process. Those are American examples designed for that. Perpetual kilns, because they go on burning. You don't finish, start again. You go on feeding the stuff in and drawing it off. They're designed so that the limestone will slide down naturally, and the fire chamber is usually separate from the basically from the kiln itself. Here's just one example, sort of thing you find in a primitive kiln in Europe. This one in Switzerland, which was operating until the 1990s. So that's where you feed the fire and we draw the limestone off at the bottom. This is a slaking pit. That's my interpretation of it. I'm pretty sure it's what it is, from the convict settlement of Macquarie Harbour in Tasmania. So this is where you put the burnt lime in, add the water, stir it up, and let it slake. Now, as I said, it's a dangerous process. There's a lot of heat and spitting, so it's worth having a masonry pit to do it in. Now I want to turn to the use of lime in, especially in concrete. And as I said, lime, it's not necessarily lime, even it can be plaster. You can make a cement out of plaster with kind of lime. The trouble with plaster is it's not water resistant, so it only lasts internally. But one of the earliest examples we have is a lime plaster floor, which is in fact a concrete floor made with lime from 8,000 odd BC. So here's that example as excavated. This one here is not a lime floor, this is gypsum slabs in paving, but with a mortar in between. And the mortar is apparently a plaster mortar. I don't know why it survived so well, because this is gypsum plaster and shouldn't survive in the atmosphere. But it's had mixtures in it, so maybe it's been made harder by mixing iron oxide in it. And here's now more sophisticated flooring. This is a Roman flooring, cocciapesto, which is red colored and has those particles in it which are meant for decoration. It's almost an antecedent of modern, say, terrazzo. So it's quite an elaborate lime concrete floor, smoothed off to give a decorative finish. And you find this one's in Malta, but you find it particularly commonly in North Africa, in Algeria and Tunisia, in the Roman settlements. Here's a more regular Roman concrete. So it's got the aggregate, which in this case I think is brick, but it can be chips of stone with a lime slurry around it. Now, turning to Roman concrete in more detail, Roman concrete is often internally very rough. This is what I might call concrete, but I might also call lime-bound rubble, when you have big stones and the lime slurry doesn't permeate it thoroughly. It's not a homogeneous mixture. And there's every gradation between rubble construction and concrete construction. Here's now Roman walling. You see the wall on the left has this rubble in this inside. The stones are brought to the outside and then it's rendered on the face. What this means is you haven't poured the concrete in, you've actually built it up. You've put the stones on the outside face, packed the rubble and lime in the middle and gone on building up to create that whole structure. So it's very unlike modern concrete in that respect. The middle diagram is more sophisticated. You've got a brick base and you've built up the sides in brick rather than rubble. But the same idea, you fill the middle in between these finished surfaces. So you would have had there a timber formwork. You would have set your brick against the formwork on either side and then packed the concrete in. Not poured it in as you would today, but packed it in. Here's now one where a arch vault roof has been formed in the same sort of material. So what's exposed on the bottom is more as continuous stonework, but behind it is lime-bound rubble. Here now is the makeup of some cement and concrete in Rome. And here you see there's different coloured aggregate. Why is that? What would it be? The name here, opus caementicum, opus just means work. So you talk about cement work or tile work and so on in these Latin terms. Well, the coloured materials here are volcanic stones, lightweight, tufa and so on, which are very good aggregate. And also you use volcanic ash in the mixture. This is what's generally regarded as a Roman invention. The Romans did not invent concrete, as people often say, but they did seem apparently invent hydraulic cements and hydraulic concrete as a result. When you mix a volcanic ash, this pozzolana, which comes from near Naples, into the cement, you give it hydraulic properties. That means that instead of washing away in the rain, if you say plaster the face of your building in lime water, it'll normally wash away with the rain. But if you add this pozzolana and make it hydraulic, it will resist water. And you can even build structures underwater with a hydraulic cement, which you can't with an ordinary common lime cement. So the Romans made quite large sort of harbour works, piers and jetties and so on, with this hydraulic cement. But going back to these materials, you can see now in that close view the two different aggregate materials and then little chips of the volcanic earth of the pozzolana within the lime itself. So there's the materials you've got. In that case, it's red pozzolana, the pozzolana rosa, and scoria from Vesuvius and also from near Rome, and the yellow one at the bottom. And here's now the sort of first phase of Roman sophisticated concrete. On the outside, it looks like a rubble wall. People have sort of stacked up, if you like dry stone perhaps, stacked up irregular stones to create the face of the wall. But that's just the face of the concrete. They've done just what I described to you before. They've packed, there's another example, see it's broken away. You can see inside that, it's rubble, it's rubbish. It's only the face that's got that nice set sort of drywall effect. So they've built the facing up inside the timber formwork and then packed the rubble and cement in between it. And this is called opus incurtum. This is irregular work, essentially, opus incurtum. The coins, the edges and corners are done in regular stone because, of course, you can't really build that to a corner. This is the next phase, opus reticulatum, where instead of seeing irregular stones, you're seeing square blocks in a grid. It looks like a network, like a net, hence the term opus reticulatum, which means netted work. Reticulus is networked. But again, this is the face of a rubble concrete wall. The difference here is that those square blocks are tapered, so they point inwards. So they will actually bond into the rubble concrete well. That's the purpose of the shape. And they were first made in, they're cut from stone and later on made in terracotta to suit. Another example of opus reticulatum. You can see at the bottom where it's been taken out, the indentations where the points of the blocks ran into the rubble concrete inside. Here's just a close version of it. And here you see the same issue. When you get to the coins, the corners, you've got to build up in squared material because you can't take that to the outer edge. So there's the comparison of the first two, opus incurtum and opus reticulatum. The third one, opus tetrachum, is made to look on the face of it rather like brick. It is in fact terracotta pieces. They're not bricks, they're triangular. They're shaped like a half of a sandwich. But they do the same thing. They point in, that shape means that they point in and bond with the concrete in the middle. It's often quite hard to tell whether you're looking at a brick wall or an opus tetrachum wall because the face looks exactly the same. But there's an example. You can see the triangular shape which points into the wall, body of the wall. This is just for comparison. See the same sort of thing being done in Aztec work in Mexico. You have what looks like a solid masonry vault, but the pieces you see are sort of L-shaped and they key into the rubble concrete behind. Now I want to turn to the idea of vaulting, what I call the homogeneous concrete vault. And it's a bit hard to describe it because most of you don't see it. But here's an example where you have this temple base, and although the face at the end appears to be obus incurtum, the whole of the structure beneath the grass is solid concrete, and it's forming arched vaults, barrel vaults, cylindrical vaults over the spaces below. And here you see how it might be built. But in this case, they've made the formwork, which is timber, and they put onto the timber tiles. And the tiles are going to stay in the concrete. So when you pack the concrete in and you get to pour it, you pack it into those compartments. The brick ribs provide a sort of armature, and then you just pack the concrete between. You end up with the sort of homogeneous concrete and brick substance with the tiles on the face below, so you don't see the concrete from underneath at all. In fact, this is perhaps an exaggerated version of the formwork. Formwork is expensive and difficult with early tools, with elaborate timber working, and often you place those tiles in a much more irregular timber system. It's a way of providing a true face for the concrete without having to build the timber accurately. There on the left, you've got a continuous formwork forming the concrete, but on the right, you see there's not continuous boarding. The tiles have been placed straight onto those slats to make the concrete, to make the face of the concrete, I mean. And then you end up with these buildings here, which I think are quite extraordinary. These are exceptional. Most when we talk about concrete vaulting, we're talking about Italy, or especially Rome itself. Across the Roman Empire, practice was very varied. But this is one place where they made true concrete. Now, this looks like a World War II air raid shelter or something, but these are baths. It's quite a luxurious building. They're the hunting baths because the hunters who collected the lions and giraffes and so on for the Roman amphitheatre were a well-paid guild who operated on Africa, and this was their resort headquarters. Inside it has bars and mosaics and so on. It's a sort of country club out of which they go to do their hunting. And it's all made in this solid concrete vaulting, a very modern-looking character. You see, you not only have barrel vaults, which are sort of standard, but in the middle, what's called a cloister vault, built up like a cloth cap, curved segments joined together. I'll come back to that a bit later. Here now, an elaborate building in Rome, even more elaborately shaped, the Minerva Medica. It's a so-called temple, but really it's a garden temple. It's a sort of place where you might go and have picnics and things rather than a really religious temple. And it's built up in a similar way to what I've described, with brick ribs and then the concrete packed in between, as you can see on the right. And in the ruins on the left, the brick ribs have survived and the concrete has washed out. It's probably common lime concrete, not with pozzolana. There's the plan of that. And if you look at the concrete in detail, you can see there the traces of the brick ribs, but also pots, amphorae, which are the Roman vases. They're vases used for transporting things like olive oil. And once used, they tend to be scrapped. In this case, they've been put into the vault. They serve to lighten the vault, but also in some cases, they tend to be used to give it acoustic properties. In this case, probably just to lighten it. Now, of course, the greatest example of Roman concrete construction is the Pantheon in Rome, of which the whole structure, apart from the portico on the front, is essentially of concrete, or brick and concrete. So there inside it, the lower parts are all faced in marble, but above it you see that wonderful semicircular dome with coffering, that is those recessed panels. And those recessed panels have been formed in part by the timber formwork of that shape and in part by building the layers in brick before you put the concrete on top of it. I'll come back to that in just a moment. The interesting thing about this is that that top is hemispherical, it's a half sphere, but the coffers aren't pointing towards the center of the sphere, they're pointing down towards the ground. You see how the sort of overlapping of the panels is skewed downwards. And the idea is that the whole dome focuses on the center of the floor where the emperor would sit. So that's a sort of visual way of emphasizing the importance of the emperor at the middle of the building. There's that wonderful concrete dome. And some details, you can see on the left, especially the way those panels taper downwards. Now, this is a huge dome. It remained for a very long time the biggest dome in the world, and it exerts, of course, an outward thrust. Remember, we talked previously about how an arch pushes outwards. And here, it's contained rather ingeniously. But first of all, Now you see some of it stripped. You can see how in those panels they've built the ribs up in brick, and indeed a couple of the layers go up in brick, and then the concrete is behind that. So that's the basic structure of the dome. Now here is a half section, and that vault will normally push outwards and the whole building will break outwards. Now what's been done to stop that is a couple of things. First of all, lightweight material has been used, especially in the upper parts, so the weight that's going to create the outward thrust is reduced. There's a hole at the top, an oculus. The function of that is actually not to lighten the dome especially, but it does that. The function of the oculus is to let in light into the building below. So they didn't rely on artificial light. They had this oculus, which means an eye, circular opening, and although the rain gets in, it disperses over a large floor below, so it's not usually a big nuisance. But at the sides there, the wall is thickened. You see the sort of chambers and spaces, and that gives a line, a space down which the line of thrust from the vault can go without breaking the whole building open. I need to have really a diagram to explain that to you, but the whole purpose is to contain the thrust effectively. And you can see in that key the different materials used at each level. Ideally, where the dome ends and the wall begins, that's the haunch part, the dome is thickened, that part wants to have weight. That's going to improve the resistance to the thrust. So using brick there rather than lightweight material. Now, turning to cruder concrete vaults, generally outside Rome, much more common in places outside Rome, are these cruder vaults. This one here in Pergamon, Turkey. This would be very difficult to form with conventional formwork because it's an annular vault. So it's circular and it's curved in two directions, of course, which you can't do with straight timber. So you don't know exactly how they did it, but you can see it's actually a very crude material structure. It's a rubble vault going around that annular shape. This one here is a later Roman vault. And you can look at the top, that's sort of chopped off, but that was a dome central chamber. And there you see it from inside. So here you have, this is in what's now Iran, ancient Persia, Firuzabad. Again, the oculus being used in the Roman fashion. This crude vault, though, is actually very comparable with another structure in what's now Croatia. Same system exactly. Now, Croatia is just across the Adriatic from Italy, so it's virtually almost a part of Italy. And in fact, the building we're seeing here was the palace of the Emperor Diocletian, which he built when he retired, just as it were across the road in what's now Croatia, the palace of Diocletian at Split, or Spalato. And so we're seeing how the building techniques here are the same at distant Persia as they are in the Adriatic coast. Here now in Syria, something different. This is not a circular vault, this is a square base, so it has to be sort of fudged in a way, and it's creating what I described before, a cloister vault. So each segment from the wall is coming up in a curve, but it doesn't, it's all on a square plan. A planned section through this would be square all the way up to the top. And as we move into the early medieval period, early Byzantine period, this is the 6th century in Turkey, you have here what looks like a very conventional masonry building, except when you get to the vault, it's still rubble concrete. But it's even more than that, because here's another example in the same area. When you take the stone off the wall, it's still got rubble concrete behind it. It's very common in medieval work, right across Europe, to have what looks like stonework that's filled with a crude lime concrete inside the wall. Here, this is the Greek island of Santorini, and it looks like, this is of course mostly now modern occupied houses, but they have some age, look like a whole string of ordinary houses down the terrace. Most of them though are built into the hillsides, sort of caves, with a structure on the face of it. And the structure on the face is built with arched vaulting of various forms. Typically, just perhaps the top left-hand would be the most typical form, just a curved vault coming out from a sort of cave behind. But they are built in a way which is often very crude. There's some broken down ones. And they're built without using elaborate carpentered formwork. They use in this sort of vernacular fashion. So you make a framework with these rough timbers, and then you build it up with reeds and other material to make it smooth, probably with plaster then, and then you place the concrete on that, to get a true surface. And it's possible that much of the Roman work would be done in a similarly ad hoc fashion. We just don't know because we haven't got the evidence of surviving formwork. Interestingly enough, this traditional technique in Santorini was being used in just the same way in the mid-20th century here at Capri in Italy to create those very thin rubble vaults. Now looking at an example in England. At the top, again, this would be what looks like a stone building, but inside it, it's a very crude rubble concrete bound in lime. It's common lime, not hydraulic lime, the cheapest possible material. And at the bottom example in Cyprus, a very sophisticated medieval building, early Gothic building, but the whole interior of the structure of the vaulting is in fact rubble concrete. Now to turn to so-called Roman cement. I described to you before how the Romans used pozzolana to improve the quality of their cement and give it hydraulic properties. So the ordinary aggregate, the ordinary fine aggregate would be replaced by this volcanic ash, which gave it this special property. In the late 18th century, people in France and especially in Britain discovered cements which had the same sort of quality, same hydraulic quality. They weren't made with pozzolana. Some attempts were made to use pozzolana in Europe, but these were not. They were made from a particular lime which burnt to give these properties. And they call it Roman cement by reference back to Rome. It's a misleading term because it's not, in fact, like the Roman cement at all. It's based upon septaria, which are naturally occurring lime deposits, which are impure. They're mixed with clay. And if your limestone has clay in it, it doesn't burn as easily to make a lime. But if you burn it successfully, you have to use a higher temperature, and you may get lumps in it, which are best to be ground down, but you get a lime with hydraulic properties, capacity to resist water. And there's every gradation now from common limes through this hydraulic lime, so-called Roman cement, natural cement, which occurs because the stone naturally has these materials in it, to artificial cement, where you actually choose the components and you mix the cement you want before you burn it. And that's what's done in the late 19th century in artificial cement works. So let me make this clear. To make a good hydraulic cement, you have a mixture of lime and clay, which at first was found naturally in various locations, and in the end was mixed ideally, and chemists and so on worked on this to give ideal proportions. So this is an artificial cement, is what we generally call today Portland cement. Now making this into concrete was done in various ways. There's a different tradition in France than in Britain, which I don't want to go into any detail, but there's an example of French concrete being mixed. That's termed béton, which is just the French equivalent term. And here you can see that they managed to make a béton which is hydraulic, which they're doing on the left an underwater structure. They built a timber caisson, they're putting concrete into to build a pier for presumably a bridge or something of that sort. But the French got so far by the 1860s as building a complete concrete building. So now getting concrete being used as an architectural material. This wasn't regarded as cutting edge desirable. This was in fact a cheap way of building a church in one of the less favoured suburbs of Paris. Nevertheless, a radical and important development. Now bear in mind all the time I'm talking about concrete, not reinforced concrete. There's no reinforcement in this, or if there is, there might be some iron, scrap iron put in just to stop shrinkage cracking, but no scientific method of reinforcing concrete buildings at this stage. And here's some British concrete at the time, so-called rock concrete, but essentially just the same as we've been talking about. It's in this case got a natural cement binding the aggregate. Now, the formwork is another issue which is worth considering. We've looked at fairly crude formwork so far. In the 19th century, the idea was developed of having a formwork which could be not just built to the shape, then taken apart and maybe reused, but actually kept on the site and moved up the building. So you might form the bottom, say, metre of the wall, and then you might move the whole formwork upwards to make the next metre height and so on until you've completed the height of the wall. And that's the basis of this patent apparatus by Joseph Tall in the 1860s. And there were various other versions of this idea. And here's an example in Australia made with a local patent by the Queensland architect C.L. Dupree, who basically adapted the Tall's patent for use in in Queensland. You can't see anything about it here, but that's how that house was built. And especially useful, though, for industrial chimneys and for structures like silos, which have the same simple shape going vertically for a long way. And that's your two different systems. One is jump form, where you take that piece of formwork and you form the concrete in it, you let it set, take the formwork off, set up again and form the next layer. But the other is slip form, where you actually don't totally remove the formwork at all, you just move it up, you loosen it and move it up, keep on casting continuously as you rise. And these silos in New South Wales are built by slip form. You can see the formwork on the top, which is still in the process of being moved up as the silo is cast. And here's a housing system, cammerated concrete, which is in fact essentially slip form. It's exposed here, but the wall has cavities in it, and they're made by square steel cores, and the steel core is moved up with the formwork on the outside until you end up with a full height wall with square cavities running right down through the wall, which give it better insulating properties, reduce the amount of concrete you need, and possibly reduce the amount of moisture likely to go through the wall from the outside. And here now is the idea turned horizontal. This silo is being cast by moving the formwork along horizontally, so slipping horizontally rather than vertically. Now, turning to the idea of reinforcement. As I said, what we've seen so far has not been reinforced, certainly in any scientific way. There were early attempts to create some sort of reinforced work. This one here in Paris, the Toisonnet system, was developed because there was a strike of carpenters. It became impossible to build timber floors in Paris. So they developed this plaster floor, which is based around square wrought iron rods, wrought on malleable iron. You remember the distinction, wrought iron rather than cast iron. So you've got an wrought iron joist, you've got a flat bar spanning across, then square bars on that, and you set all that into a concrete, which in this case is made of plaster, not of lime or cement. But then, around about the same time, the gardener Joseph Monnier, who made flower pots commonly, put mesh into his flower pots to reinforce them, and conceived the idea of using the same thing to make drain pipes. So he created a drain pipe which has mesh right around it and concrete on it. Now, what is this doing structurally? Is that mesh taking compression or tension, or what is it doing?
Tension.
Well, if anything, probably tension, but you really can't analyze this. So this is not scientific reinforcement. It's strengthening, and it works, but it's not scientific in any sort of real sense. The other question I would ask you is, why would you shape a drain pipe in this oval shape rather than circular, or has it just been distorted during the casting?
Similar to an egg form, which is meant to be, the strongest naturally occurring form, isn't it?
Well, it's an egg form, it's an ovoid form, certainly, but what's the benefit of it? You say it's natural, but not as good structurally. A circular is the best shape for resisting compression in a shell like this. It's practical. This is a drain pipe, sewage pipe, and that shape means that the flow of the water is sharper at the bottom and it moves the shit out effectively rather than all building up. It's the purpose of these ovoid drain pipes. I'll ask a question. And so you get from this time onwards sort of semi-reinforced structures like this aqueduct, again the same period, the 1860s in France. Another reinforcement aspect is this, expanded metal. Now let me explain what this is. You'll see this around commonly, but you may not know what it is. Expanded metal is made by taking a sheet of metal, look at the bottom diagram, putting slices into it, slashing into it, and then pulling it out. So you create this diamond pattern. So one sheet creates this rather complicated shape without any wastage. And that shape then is a very useful material. This diamond lattice is good for plastering. So you can put the plaster in, this is the inside, so the plaster is pushed in from the other side and smooth. The plaster goes through and keys in to make a very good structural form. So in the past you used timber laths for plastering. This is a much improved and simpler method of plastering. So that's the first use of expanded metal. But then the idea was conceived of using the same material for a structural concrete. There's just a curved ceiling made in that way in America. But here now is the first attempt to test this in a slab for structural purposes. So 1897 is the critical time when expanded metal is used to reinforce concrete. Again, not totally scientifically, but just because it strengthens it in a fairly effective fashion. And here you see examples of ceilings being built in this fashion with ribs and so on between them. So from this time onwards, expanded metal is one way of reinforcing concrete. And here's an example in France. Metal déployé is the same thing as expanded metal in English. Here's a proposal for using it in sidewalks, footpaths, and even in lighthouses. I don't know if anyone actually built that way. This is part of the advertising material of the expanded metal company. However, it's only when you begin to place your reinforcement in accordance with the needs generated by compression and tension that you get something approaching our modern idea of reinforced concrete. And that's what I want to turn to now. This is a very interesting example because this man, William Wilkinson, was a plasterer in the north of England. He took out a patent which, as you see here, 3 different forms of reinforcement. And they're very important, except that he was forgotten. This great advance was forgotten afterwards. It doesn't form part of the real history of reinforcement at all because nobody knew anything about it. But forget the bottom one, which is not all that good. The top 2 have a cable draped across the span. And because the cable is draping down the middle where the bending moment is highest and rising over the intermediate supports where the bending moment becomes negative, rather like what we discussed when I was talking about iron beams, this is a very effective way. The cable is almost the ideal place to take the tensile stress in the concrete. On the top right, just note those little circles above the cable. He's put in hollow pots there, which I suppose not only lighten the slab, but perhaps help keep the cable draped into its proper position. But just bear this in mind, because I say it's forgotten, but something like it appears later on. There's that. Oh, and that's that question. This just explains the point I was making. So with a simple span, that simple drape at the top would be effective, but with a negative bending moment, turning the cable over the top is better. Now, there are now a number of empirical developments. That is, there's no big scientific push to develop these ideas for a couple of decades, but there are various people who are making concrete structures with some level of reinforcement in them. We don't know exactly how this building, for example, it's quite a large solid concrete house. It has reinforcement in it, but we don't know how it was placed, certainly not in any scientific way. Often they use things like old railway lines for reinforcement because they're available easily. This one here was made by the famous British architect Richard Norman Shaw for the jury house at the Paris exhibition, and was actually coloured red to look like brickwork. So it was not a very advanced idea, but it was made in precast concrete by W.H. Lascelles, a London builder. And you now get this man Thaddeus Hyatt experimenting in various ways with putting iron in and actually testing it to see what works. This looks not unlike that Toasne flooring system I described before, with the plaster set around bars and rods and so on. This is just one of many tests which Thaddeus Hyatt did. Then in America, this is really quite an effective design here. These units, because they curve down, get some depth, where the rods are placed for taking the tension, and the thick part of the arch is taking the compression, so it's quite a scientifically disposed system. These are all precast units, and these were being made, essentially the same thing being made quite commonly in, for example, Melbourne into perhaps the 1960s as a regular flooring system. That building, though, once again on the outside, doesn't look very strikingly modern, although the structure was so advanced. Here now is E.L. Ransom, who's a prominent engineer in America, who immigrated from Britain, and he's quite important. This bridge here, the Albert Lake Bridge, has some form of reinforcement around the arch. So it's a concrete bridge, looks like stone on the face. It's a solid concrete bridge with some form of iron reinforcement in it, which we don't know exactly what it is. I'll show you a couple of bridges soon that we do know, which do the same sort of thing. So what function would the bars perform? Bars around the arch, what do they do? Take compression, tension, shear? Well, they would, if anything, take compression. On the other hand, the concrete arch is probably strong enough without them to take compression. So it's hard to know, what the purpose of this would be. Here now, though, we're getting to systems which are a little more logically designed. This is the Wunsch system designed by Hungarian engineer Robert Wunsch. And he has now placed a bar around the arch and built up almost like a frame or a truss above it. It's the bar around the arch is important to reinforce it. And as it's over a larger span now, it has perhaps some structural use. And this is the major example of the Wunsch system, the Emperor Bridge in Bosnia, built by Robert Wunsch in 1897. So on the outside, it again looks like a conventional stone bridge. That's a concrete bridge where you see the iron components on the bottom right, which frame up inside the concrete. Now, what's interesting, although this was the best known, greatest example, the biggest example of the Wunsch system took place in Australia, only around about the same time, in fact, slightly earlier than that Sarajevo Bridge. This is the Lamington Bridge in Queensland. Although the spans are much smaller, there are 11 of them, so it's a huge structure on the Wunsch system. Alfred Brady, who was a government engineer, was an innovator and must have discovered this in the literature and he also discovered expanded metal and began doing advanced concrete systems using these European ideas. So there's the Lamington Bridge over the Mary River in Queensland, and you can see the Wunsch bars which reinforce it. The other system was that developed by Paul Milan in Europe, but then taken up most especially in America. And he uses not a solid concrete fill with the bar around it, but an arched concrete fill. So in this case, above the arch would be just dirt or other inert infill, unlike the Wunsch system. And he uses here something like almost like a sort of girder, but he can use simple bars in the same way. So this is the Milan system. He developed some sort of fairly crude ways of calculating the amount of steel required too. Here's a rather more elegant one in America, this tapering form. There's one with just a bar being used, but still again is the same Milan system. And that bar is again probably a piece of railway line, which is the common material to be used. It says I-beam, so maybe it's true I-beam, I don't know. Now, there are a number of other systems. This is a period of great, I'm talking mainly about the 1890s, great experiment, not always fully scientific. I mean, the means of calculating steel and concrete were not really developed. So you get French people like this man here, Boussiron, one of many. Here we have two systems being advertised. The Bonner system, Italian system, well, Bonner was practically in Paris, but in Italian, on the right. But on the left, interesting, is the Conc system. Now, the Conc system is not a pure concrete system. It's a combination of brick or tile with concrete. And it was used especially by the architect Anatole de Bordeaux, who's quite an important French architect. And this is his book on using what he calls ciment armé, which is reinforced concrete, but in fact, based on this Conc system. Here you see on the left, a column built up with brickwork, perforated brick, with wires running through it, and then rods in the middle, and the middle is filled with concrete. So it's a combination of brick and reinforced concrete. Form of the slab, which is a bit like the Bonner system, in fact, the slab system on the center. So it's the slab system. There's the column system. And he uses it to build this rather wonderful building. Again, it looks like brickwork on the outside, but the main structure is concrete. And it's concrete which is placed with diagonal ribbing. So it's not a conventional square bayed system. The ribs run diagonally across the church. And there you see it inside. Really interesting, I think, aesthetic effect and very advanced in concept. Does anybody in this class live in college, particularly in Newman College? Because if so, this might look familiar to you. Here's I'll come, you'll see that in just a moment. Here's another scheme for a dome by Anatole de Bordeaux using the Conc system. And here you are in Newman College showing a dome with intersecting ribs, which has been inspired by this. It is not built on the Conc system, but it's inspired by the works of Bordeaux. He's there. This is the refectory, the dining hall of Newman College by Walter Burley Griffin. Now, science reaches us with the Monnier system. You remember I mentioned the Parisian gardener Joseph Monnier, who made flower pots with mesh in it and then developed the drain pipe. He was no scientist at all, but he sold his patent rights to Germans, Weiss and Bauschinger, who then experimented and developed his reinforcement into a more scientific system. So you're seeing here the Monnier drain pipe, and the Germans go on making these drain pipes even after they've acquired the rights. And here is the Monnier system now made more scientific. You see Weiss, who wrote this book, the patentee of the material in 1887 in Berlin. And it includes within it not just the drain pipes, but new forms. Now look at the top one. He's got a concrete slab resting on wrought iron joists. It could even be steel almost by this date. And that sort of cable going up and down just the way Wilkinson did in England previously. So that forgotten system has now been revived by the German Weiss. The bottom system is quite scientific, but not perhaps as effective. It's almost like a lenticular truss because you have bars arching upwards for compression and arching downwards for tension. If you remember me talking about George Stephenson's Gordon's Railway Bridge, it's doing almost the same thing. And in particular, they learned how to analyze these stresses. So this is approaching really the way you'd analyze a slab or beam today, with the moment of inertia for the concrete and compression at the top, but at the bottom, of course, only the steel is taking the tension load, setting a moment between the two. And the Monnier system now is more and more scientific because the rods are being placed at the bottom where the tension is, then jacked up at the top where over the points of support where the negative bending moment occurs. More and more like modern reinforced concrete. And two other engineers, French engineers, develop along the same lines, Coignet and Ennebeek. The Ennebeek system, very similarly, the rods are at the base of the beam, they jack upwards over the point of support. He uses a lot of stirrups, those straps holding the reinforcement together. From a practical point of view, for the historian, often it's easier to tell these systems by looking at the external appearance of them, because the Ennebeek system often has these rather steep haunches, the tapering part below the beam, with chamfer stops, that chamfered off corner. So often looking at a structure, the first thing that tells you it's an Ennebeek system is looking at those visual details rather than being able to look at the reinforcement inside. But the Ennebeek's analysis is even more sophisticated than Monnier's, because the neutral axis is now taken to vary in height. You see in the bottom diagram. And here are various details of the Ennebeek system, an arch version, and that's the standard post and beam, column and beam version of the Ennebeek, as patented in 1887. He also developed this hollow block system, hollow tube system, it's called here. So you have a complete horizontal formwork for your floor. You place onto it these hollow blocks, which may be often terracotta, often also plaster. You then drop your reinforcement in between the blocks. And when you pour the concrete in, you've got essentially a ribbed concrete slab. So the hollow blocks have no function except to just keep the concrete apart. They stay in place. So you end up with a horizontal ceiling, but the structure is really a ribbed concrete slab. So there are various versions of that. There's the Ennebeek one at the top. What becomes a standard one in Britain below, the BRC, which is the British Reinforcement Company, hollow floor below, doing the same, really the same thing. All these innovations get brought in, and the patents expire, and then they diffuse into standard practice. And in the British system, a patent normally expires in 14 years. Sometimes you get a special right to extend it to 21 years, but normally 14 years. The French systems will vary, but the same sort of thing occurs. So what were innovations in the 1880s and 1890s, by about 1914, are becoming common. And so a standard reinforced concrete practice emerges, and also engineers work out how to calculate steel on the strength of steel and concrete in a uniform basis, so that the sort of standard form of calculation develops at the same time. This now, again, you can see this is an Ennebeek system by looking at the shape of the column heads with the chamfer stops. This is a bit harder to tell. It's a very interesting example. This is now, it's a printing works, so it requires good light. So it has a sawtooth roof, which in the northern hemisphere faces to the north, in Australia it faces to the south. So it's very sophisticated, complete sawtooth roof reinforced concrete system. Many buildings made of concrete are quite functional and therefore look quite modern. This is Ennebeek still, spinning mill at Tukwara. Just really all concrete but for the glass. And I'll come back to buildings that look like this in a moment. But Ennebeek's own house is designed to show off his system. So it has these elaborate cantilevers, spiral staircases and so on, a sort of fantasy castle. And there you see it in practice. Now, the difference between Ennebeek and, say, Monier, or the Monier system, is Ennebeek was not just a patentee, he was an international contractor. He built structures on his system all over Europe. Here's an example just to show off the system, the spiral staircase rising to the sky at the exhibition event in 1908. And there's an actual bridge built by him in France in 1899. And this one in Italy, the Risorgimento Bridge in Rome in 1913. All these are Ennebeek structures. And here, he's built buildings in North Africa which have been damaged by an earthquake. And this purpose of this picture is to demonstrate that although they were tipped up, they didn't break because they were all built on the strong Ennebeek concrete system. Here now you see a British system which is really taking those elements, and the British reinforcement company I mentioned before, and these are now becoming standard ways of designing in concrete, not subject to major patents. This is an order system, surprisingly prominent given how odd it is, the Kahn bar. Julius Kahn was an American architect who did industrial buildings mainly, but patented this system. The Kahn bar is, look at the top of the picture, it's a bar which is rolled as a sort of T shape, but the side flanges were then slit and bent upwards. So you can have the main bar going horizontally along the beam, and these angles rising upwards. It looks very strange, but it actually works quite well as shear reinforcement near the points of support. And you can, if you want to put an inverted Kahn bar over the points of support to take the negative bending moment. One reason for these old systems is that while all the patents are still in place, it's very hard to design reinforced concrete. You're going to be either paying somebody or infringing on their patent. So developing a mad system like this gets you around the problem of paying somebody else to build in reinforced concrete. So here's the development of the Kahn bar, this patent systems. And although the bar makes some sense in beams, that makes, I think, very little sense in columns, as shown here. But here's now the standard way of building the Kahn bar beam. And I should say, perhaps, before I go on, this system was used in building the reading room of the Melbourne Public Library with that huge dome. So it's quite an important international system. You can actually see more clearly there how those side pieces were split up from what was in fact, in this case, a flat bar and rolled. It's normally a T-shaped bar. Now I turn to mushroom head construction. This is where you have, what's a bit of stuff at the moment, you have a column rising up to essentially a flat slab, and you avoid making beams. There are two reasons for doing that. One is that the beams require formwork, and you can avoid the formwork possibly. And the other is that the beams take off head height. So in, say, a 10-story building, you might get a complete extra floor in by cutting out the height of the beams if you have a minimum required headroom, say for your forklift truck or whatever it might be. You approach this even in the Monier system in the basement. See, the basement there here is a groin vault essentially, but it amounts to being flared column heads. So you've got a ceiling height in between where you could take a forklift truck down one aisle without hitting the top. So that determines the floor to ceiling height. What happens later on is that people now make that a feature of the design, and they have circular flaring shapes on top of the columns to create this mushroom head system. Here's one in America, the Lindeke Warner building by C.A.P. Turner. Now, by making this flat slab, as I say, you've saved on the beams and you've saved formwork of the beams, you saved height. But you've had to create a rather odd system over the columns because the shear forces are very strong over the columns. So he's put in a square section, which is what's called a drop panel, and then an oddly shaped circular head below that, which is probably going to be quite costly to make. So he's lost half the benefit. He's also probably had to make the slab thicker to take all the reinforcement required, because he's putting in here, in fact, four-way reinforcement, as we'll see in a moment. So normally in a flat slab, you'd have perhaps the reinforcement going in one direction between beams. You might put it into two directions, but in this patent, he puts it in four directions. Here it is here. So he's got the reinforcement going in four directions, and over the column itself, where the shear forces are very great, a massive sort of circular and radiating reinforcement at the actual point of the mushroom head. So that's the Lindecky wall building reinforcement shown. A simplified column head. He sometimes uses various forms, but that's a simplified version. And here it is, patented now in Australia, and used quite early on for what was known as the Dover Stationery Building in the block opposite the State Library, fronting onto a laneway, Drury Lane, not onto either Lonsdale Street or Swanton Street, but it's still there today, built on this system. But here's a difference. You see here that in this case, the column is not circular but octagonal, and the head is not a flared circular shape. It's a sort of squared off, tapering, squared off cone, if you like. Why? Why would this inelegant form be used?
Is it easier to build the formwork, more efficient?
Absolutely, spot on. Formwork, circular formwork is very difficult. In more recent times, tubular cardboard is sometimes used to create formwork, but at this time that wasn't available. So building in timber, an octagon is far easier to form, and likewise even that the flared head far easier to form than the shapes which are being used in the American system. So I asked that question. But here you now see a different version. He's using octagonal columns here, and quite an elegantly flared head. This is now by the Swiss architect Robert Maillard. He does a number of elegant bridges as well as these warehouses. Now, his system is different in terms of reinforcement. Here's a multi-story warehouse. You can see on each floor how the column reduces in dimensions because the weight reduces. And the finished floor is much more elegant, I think, than the American version. But the reinforcement is only two-way. So here you have Turner's American system at the top with the four-way reinforcement and Maillard's two-way reinforcement at the bottom. There's a third system developed around this time by a Russian, but it was later and there's really no great, doesn't play a part in the history of European architecture to any extent, so I won't go into it. I now want to turn to a French engineer, Armand Gabriel Cossadère. Cossadère was essentially a roads and bridges engineer. In fact, he rose to become the chief engineer of the Department of Roads and Bridges in France, Ponts et Chaussées. And here he is testing a bridge. Now this is not strictly a bowstring form, it's a segmental truss, segmental Pratt truss, made of concrete, reinforced concrete, which is built just to test to destruction as a preliminary to designing a huge bridge on this form at Plouchastel in Normandy. And I'll show you that in a moment. But in the meantime, here's a railway bridge built on the same system. Now you're seeing it only partly formed. And the nature of the reinforcement is important here. First of all, tell me, what is the black curved element?
It's like circular rebar.
You're seeing the reinforcement bar, as you say. This is it has so much reinforcement, it's almost solid. So you can see down the bottom left, there's in fact just spiral reinforcement wound around the rods. And of course, that will be cast into concrete at the end. Then the diagonal elements have been left so far exposed. You can see the rods for the diagonals being exposed there down the left-hand side. And this is going to make a bridge of the sort we just saw. But the principle of that spiral reinforcement is this. He looked at columns. He did experiments to find that if you tightly wound the reinforcement around the core concrete, it could take greater compression. So the concrete became greater in compression by having this containment, this hooping, it was called. This was what he called béton frété, hooped concrete, which gave this greater strength. So this is the basis of Conc patent, particularly apparent in columns like the one shown here, but also in any compression member like that top curved chord of the bridge. And here it is being introduced in Australia. The name Conc was never, to my knowledge, mentioned in Australia by anybody, never published in any technical journal, and yet this odd engineer, E.G. Stone, Edward Giles Stone, seemed to discover the system and built this giant roof structure at Geelong on his system. And what it consists of is 3 bridges. You see that there were 3 bridges in parallel, each pair is joined together. So he's taking the same form of bridge that Conc had developed and reinforced in the Conc fashion in all the compression members. And this was by far the biggest reinforced concrete roof span in the world. And it was an obscure Geelong in Australia, and it's been demolished under the John Cain government as a great tragedy. It would have been a World Heritage item. But the system here has been slightly modified. The girders are not segmental, they are hog-back, that is, they have some vertical element at the end, and an old piece of bracing there, which is wind bracing, so it can't be pushed sideways. And I could go into that in much more detail. It's a fascinating structure, but I won't. I want to turn to what are perhaps the more architectural implications of these concrete developments, because they inspired designers to build in innovative fashions. Here now, this elegant ribbed structure in 1905, Liège in Belgium. And here it is, it's obviously a sort of Art Nouveau structure. Here, this very elegant, simple footbridge in Germany. This water tower, it's like a sort of space, futuristic space odyssey sort of design, 1909. And especially prominent is the top was a internet competition designed by the architect Tony Garnier, who won the Rome Prize, designing an airport with that giant cantilever on the right and the water tower on the left, rather like what we just saw. And in practice, he builds much more functional, but still all concrete buildings like the slaughterhouse in Lyon on the bottom left. And the Italian architect Sardelia, who hardly built anything at all, but his designs were fantastic designs inspired by the properties of concrete. And now this wonderful building, which is externally not great, but internally quite fantastic. This is the Jahrhunderthalle, the Centennial Hall built at Breslau in Germany, which after World War II became Wrocław in Poland, designed by Max Berg in 1913. And it was there's an overall form of it. It's a giant structure like this. The dome is now a dome bigger than of course, bigger than the Pantheon, the biggest dome, certainly the biggest dome in concrete in the world. And it's structurally separate from the base. So where that horizontal line occurs, there are actually rollers separating the dome from the base. So there's the dome at the top and the base structure below. And those are the rollers which ensure that no moment transfers from the one to the other. And there's the wonderful, beautiful skeletal dome. There's today. And theirs is compared with domes of other sorts, like the Pantheon, top left, and there's our one on the bottom left. Just a personal note here, by chance visiting this site, I was able to just put on a hard hat and go up to the top, because Poland is not within the European Union, so the safety regulations are not very strict. So the whole party just put our hats on and went up and had a look at what they're doing to stabilize the building, which is put things like these bolts through the concrete structure. Now, as opposed to those rather expressionistic buildings, now turning to the more functional buildings. There's a factory in America, not unlike the spinning mill we saw before by Ennebeck, just panels of glass set in into the reinforced concrete structure. There's a bit of a difference here. This is by the engineer Ransom, who's buildings I showed you before. I showed you his bridge, Albert Lake Bridge, and he showed you the Leland Stanford Museum building with concrete flooring. This is now his factory design, in which he's actually made the whole spandrel above and below the slab, between the lower windows and the upper windows, into one beam. So it's calculated as if that were one beam, that cruciform section. And then he builds, then in France, the architect and engineer Pellet builds flats. Basically, it's a more elegant system, but basically it's just the reinforced concrete with the holes punched through the glass. But the beauty of these flats are the interiors, because the use of concrete means that there are no internal walls. So you can divide the flat as you wish. For the first time, you've got total flexibility in planning within the apartment. And here's a garage by Auguste Perret. Bear in mind now that this is a pioneering form, because the motor car is new. The garage is a new idea. This is a cutting edge opportunity for a designer. When you look at the cars of this period, they're old fashioned and quaint. But look at this building, it doesn't look too bad at all. And even this theatre, so all the complicated cantilevered balconies and so on are all built in solid concrete by Auguste Perret. This church, a bit more historically styled, I suppose, but inside it, a very elegant system. That's the screen at the end of the church. Inside it, this very clever shallow concrete vault down the nave, and to deal with the outward thrust, he's put lateral vaults running in sideways into it. The church of Notre Dame de Nancy, which is a suburb of Paris. Then, of course, you get the great Stike Le Corbusier, obviously inspired by the properties of concrete. Often, the reality of the structure is not as simple as it might appear, but the aesthetic is derived from the simple concrete forms. And then the engineering aesthetic, where engineers design and they make a feature of the properties of the reinforced concrete. So again, Robert Maillard, whose mushroom head system we saw before with the multi-story warehouse, designs beautiful bridges, mainly in Switzerland. This one, actually on a curve in plan, as well as being a curved bridge, nice bridge. And then this hall, which takes up the idea of the sawtooth roof, but now in a wonderful shell system. Now, another designer is Eugène Freycinet in France, who builds these giant paraboloid aircraft hangars at Orly, the airport near Paris. And Freycinet is also the pioneer of pre-stressing in concrete. In Italy, the engineer Pierluigi Nervi, the cinema, and this wonderful cantilevered roof grandstands in Florence, which inspires in a way, just a slight diversion for a moment, these shell cantilevered concrete forms by Eduardo Torroya in Spain. And back to Nervi now, this aircraft hangar on this lamella system, in which all the elements are running diagonally. That's what's termed a lamella. It's almost not really calculable. It's a sort of network of statically indeterminate forms, but very strong. And even during World War II, concrete ships like this one. Here's the lamella system again, 1950, to an exhibition. And a modern example of this sort in 1980, an elegant bridge. So that's where I finished that first segment. Now, do we need to have any